Today we'll be going through the life cycle of a star and also give some examples that you may have seen before. So all stars start off as essentially a cloud of dust and hydrogen gas, and this is called a nebula. A nebula can also be referred to as a stellar nursery because they're where stars are born. Current examples include the Orion Nebula and the Eagle Nebula, which contains the pillars of creation. Over time, the attractive forces of gravity pull the dust and gas together to form a protostar. As more particles collide and join the protostar, it gets bigger. The force of gravity gets stronger, which allows it to attract even more dust and gas. The gravity squeezes the protostar in, which makes it very dense. It also means that the particles inside it collide with each other more often, which then raises the temperature of the protostar. So when the temperature and the pressure get high enough, hydrogen nuclei start to fuse together to form helium nuclei. And this is the process of nuclear fusion. So this gives out huge amounts of energy, which keep the core of the star very hot. Now, this is an actual star now, so we call it a main sequence star, and this is the stage that our sun, the one in the sky, is currently in. At this point in time, the star is in equilibrium and it's said to be stable. This is because the outwards pressure caused by the energy that's being released from nuclear fusion is perfectly balanced out by the inwards pressure caused by gravity. So this allows the star to be stable and it can last in this stage for billions of years. Current examples include our sun, Sirius, Alpha Centauri A, and Alpha Centauri B. Now this is where the process splits up a little. We'll first go over what happens to a star that is similar in size to our sun, so a medium or a small size star. At some point, the main sequence star will start to run out of hydrogen. This means that the star won't be able to do any more nuclear fusion, and so the inwards pressure of gravity takes over and it contracts the star into a relatively small ball until it's so hot and dense that nuclear fusion can start up again. In fact, the temperature would have increased so much that the helium nuclei start to fuse together to create even heavier elements, such as elements up to iron in the periodic table. The star expands to form a red giant. Current examples include Pollux, Aldebaran, and Delta Hercules. So when the red giant becomes unstable, it will expel its outer layers of dust and gas, which then leaves behind a hot, dense, solid core that doesn't do any nuclear fusion anymore. So this means that over time, it will gradually cool down, very slowly though, and the amount of energy it emits will also decrease. And this is a white dwarf. White dwarfs give off lots of light, they appear white, hence the name, and they are relatively small. Examples include Sirius B and Procyon B. So scientists predict that eventually the star will no longer have enough energy to emit light, so it will appear dark, and this is what we call a black dwarf. So there are no known black dwarfs yet, since the universe isn't old enough for any white dwarfs to have cooled down to the point where they become black dwarfs, so this makes black dwarfs purely theoretical. Now let's talk about stars much bigger than our sun. To start off, it's pretty similar to red giants in that the stars run out of hydrogen and then they will expand. These big stars form red supergiants. The helium nuclei still fuse together to produce heavier elements. Examples include Betelgeuse and Antares A. Red supergiants will start to shine brightly again as they undergo even more nuclear fusion. After passing through several cycles of expansion and contraction, they will eventually explode, and this is a supernova. Supernovas form elements even heavier than iron, which is something nuclear fusion and red giants cannot achieve. And these elements are then ejected all across the universe. So that's where elements heavier than iron come from. During the explosion, a supernova remnant is created since the explosion causes gas and dust to be compressed in the surrounding areas. Hopefully this sounds familiar, since these remnants can form a new nebula, which is where new stars can form, hence the name life cycle of a star. Now the process splits up here a little again. And now if the star was just very big, still big though, it will condense into a very dense core called a neutron star. The name comes from the fact that they consist of neutrons, which are densely packed together. Examples include the Crab pulsar and the Vela pulsar. And in case you are wondering, a pulsar is basically a rapidly spinning neutron star. Now, if the star was massive, then it might collapse in on itself and become a black hole. Now, black holes' gravity is able to pull in any light that passes near them. So this means that they will appear as empty spaces or tiny holes in the universe where no light is ever emitted. In fact, at the center of our Milky Way galaxy, there's a supermassive black hole, which is called Sagittarius A. So that is the life cycle of a star. Yeah, thank you.